I'm going to explain how example 3 modifies a function return address by directly manipulating the stack. First, look at the code. The most interesting and the most important part is here. This code moves 12 bytes forward from the beginning of buffer 1. That address happens to be where the return address is stored on the stack, and the program adds 8 to the return address, causing the function to return a different instruction. Now let's examine the assembly code of main. The call instruction pushes the return address onto the stack. In this case, the return address is this 4A8. Normally, after the function finishes, execution returns to this line 4488 this line. Then the next instruction execute will be 48B this line. And this corresponds to the x assigned one assigned to x. Now let's see what the stack looks like inside the function. After the function block executes, push EBP, move ESP and sub 0x4. The stack frame looks like this. The argument will be pushed from right to left, 3 to 1. And the buffer 1 is allocated closer to the saved frame pointer and the return address. Also, buffer 1 is declared for 5 characters, 5 bytes. The compiler aligns memory to 4-byte boundaries, so it actually occupies 8 bytes. The return address is located 12 bytes above buffer 1. That is why the codes use buffer 1 plus 12 to reach the return address. Next, the statement pointer return plus 8 modifies the stored return address. After modification, return address 4B2. This means that when the function returns, the CPU jumps directly to 4B2 instead of 4A8. As a result, the assignment 1 assigned to X is skipped completely. So the value of X remains is 0. Finally, the X prints is the result of 0 instead of 1. This example demonstrates an important concept in stack-based attacks. By modifying the return address stored on the stack, a program can redirect execution flow to another location in memory. This is fundamental idea behind classic stack smashing and buffer overflow exploits. Thank you.